This video is on first order integrated rate laws. A first order integrated rate law is this rate law down here integrated. The difference between the two rate laws is the integrated rate law, it gives you time with concentration, whereas the rate law gives you concentration with the rate. Now, integrated rate laws are determined experimentally. The way they're determined is by recording the concentration as time passes. Now, first order reactions can be recognized because they have a definite constant half-life. In other words, if it takes a certain time t for half of something to change into something else, then it will take the exact same amount of time for it to go from a half to a quarter and from a quarter to an eighth. You can often see this in the data tables or see it graphically. Okay, for example, in this data table 13.8, okay, what you can see is after 600 seconds or so, right, it goes from 1 to 5 to 5. Well, 0.517, it gets halved, right? So it looks like about 600 seconds for a half-life. You can see that because if you go another 600 seconds, go to 1200, you see it's at 2.67 times 10 to the minus 5, which is about half of 5 times 10 to the minus 5. This thing has a regular half-life. It's probably first order. I can also see it graphically, right? So I can go up to 600 seconds. I can go up to the half point here, which is right here, and go out to line. Oh, it's about 600 seconds or so, right? I can then go out again to half of that, which is somewhere around here, and go, oh, and that's at around 1200 seconds. So it's having around, it takes about the same time to half, and if I were to go out to 1800 seconds, it would half again. Now, sometimes you can do that, sometimes it's really obvious, and other times you have to do something else, and that is take the natural log of the concentration and graph it. Now, since when you natural log things and they're less than 1, you're going to get a negative value. Your scale is going to be a little different. It's going to be like -9, -9.2, -9.4, like you see right over here. Okay. Now remember, for those who don't remember how natural logs work, okay, e to this number, -9.2, is the anti-log. If you do that, you go back to getting the concentration. You should be able to go back and forth. The natural log of 1 times 10 to the minus 4 is equal to -9.2. E to -9.2 is 1 times 10 to the minus 4. Now, there's lots of forms of this integrated rate law. There's ones that I like. I particularly like equation number 2. Occasionally, I might use equation number 3, but not very often. I like equation number 5. This one's very useful right here if, let's say, you want to know the time, equation number 2. Okay, because if you know the concentrations before and after, you just take the log of this fraction here and then just divide by k, and it'll give you the time. It's really easy, right? For number 5 is useful. Well, one thing to recognize is it aligns with the graph. Okay, it looks like this is the equation of a straight line. It's y equals mx plus b. Note, again, k, okay, is the slope, okay, negated, because k's have to be a positive value, because obviously this line's going down, obviously it's a negative slope, but if you negate that slope, that gives you this value here, okay? But it still gets a negative in front of it in the equation, but the actual rate constant's a positive value. And that's important, because when you stick the numbers into the equation, if you do the math in this part of the equation, it will subtract from what the original concentration was, which will give you a smaller final concentration, y. As time elapses, the concentration should decrease, so ln of AT should be a smaller value than ln of A0. All right, let's do a problem here. I'm going to do the first problem. I'm going to involve this equation here, and the second problem I'm going to involve using this equation here. Here we go. So we have our chemical reaction. A turns into 2B plus 3C. We're given the rate constant is 0.00693 s to the minus 1. Note, no molarity. It's first order by the units. You can tell that at 20 degrees Celsius. Remember, if it was a higher temperature, the value K would be larger. If it was a lower temperature, the value K would be smaller. We have an original starting concentration of 0.100 molar, and they give you a time. Note that the units here match. That's important. If they give you minutes, you better turn into seconds. It's got to match the rate constant. And that mess up happens all the time. Okay, so if they give you minutes, you better multiply by 60 to get seconds, or vice versa. All right, I'm going to use this equation, which I've written here, and I'm going to plug the values in, right? So I've got negative KT, so I get negative. Now I'm going to have ln. I want to know what the concentration after 150 seconds is, right? I know what the original concentration is, so I'm solving for AT. So I get ln of A, T, my equals negative 0.00693 times the time, which is 150. Notice the seconds would cancel out, but I'm not going to put them in there. Okay, plus the natural log of the original concentration, which is 0.1. And what I've done here is I've done the math over here, like I did this times this, which gave me, I think, I'm pretty sure, I don't know which value was which, honestly. Um, I'm sorry, I do. This times this is this number here. And I'm going to add those together, and that's equal to ln of AT. So I can add those two numbers together. So 1.040, right? Clear, 1.040 plus 2.303 equals, so I guess 3.343, and that's going to be equal to AT. I'm anti-logging it essentially, right? And when I do that, I get a concentration of 0.0353. Now that's the concentration. That's the concentration of A at time t after that time of 156 seconds has elapsed, right? They don't have to ask you about that concentration. No, they could ask you about the concentration of one of the other things in the equation, like they could ask you about the concentration of B or C. And for this, since we know how much A has changed, and we assume that these guys both start at 0, right, we can figure out what their concentration is at time 150 seconds, right? If I take the 0.1 that I have here and I subtract from it 0.0353, I get 0.0647, 0.0647. That's how much, that's the change in A, right? And what we know is that if we take the change in A over time, that's equal to 1/2 the change in B over time, right? And so and when you cross multiply, right, all we have to do is multiply 2 times the change in A, and that will be equal to the change in B, won't it? So if I multiply this by 2, I'm doing my calculator times 2, I get 0.1294, 0.1294, and that would be the molarity of subs. Oh, I'm going to make that B. I messed up my video. I'm not going to redo it. If I wanted to get C, I'd have to triple it. Sorry about that. Okay, time 1 times 1.5. Yeah, times 1.5. Yeah, it would be 0.19 something for C. I messed up on that. All right, another type of question they get is how much time does it take for 95% of something to be consumed? In this case, I'm going to use the other equation, equation number 5. So I'm going to take the natural log, and this has got A0 over AT, right? Now, since 95% are consumed, that means there's 5% remaining. 5% is just 5 over 100, right? That's what a percent is. It's a fraction over 100. So 5 hundredths remains. This is the original concentration. This is at time t. And that's equal to negative 0.00693 t, right? And again, that's this equation. I'm just going back showing you that's this equation right here. Okay. Now, if I do that, I can take the natural log of 500, so natural log of 0.05 if I want to, I'm going to write 0.05, natural log that, and I get negative 0.2996, and that's equal to that. And then I can just, the negatives will cancel each other out, so divide by 0.00693, and I get 432 or so seconds. Okay, which makes sense because, you know, after 150 seconds, right, we went down a little more than that. We halved a little more than 1/2 life. To get 95% gone, it's going to take a lot more time for that. It's going to have to halve several times, like 4 to 5 times, which is about right. Speaking of half-life, let's talk about that. We can manipulate this equation very easily to figure out the half-life, okay? Because if we take the natural log of 1/2, we get 0.693, right? So if we, at any time you want to figure out the half-life, okay, if you have the value of k, you can do that. So for our previous thing, right, if you natural log 1/2, you get negative 0.693 every time. So that, and you'll always have that. It will always be the same thing. So there's no reason to do it over and over again. The half-life is always the natural log of 0.5, which is always negative 0.693. So you get negative 0.693 equals negative 0.00693. That was from the previous page times t 1/2. And so if you do the math here, 0.6, I think you get 0.01, but I just want to mess you up here. Divided by 0.00693, I'm sorry, you get 100. So the half-life here is 100 seconds. Oh, I did mess up almost, right? And that's it. Half-life is very easy to do for first-order kinetics.